Haha! Good morning, lovely people. I bet you were missing my unshaven face. Well, here I am. I hope you're keeping well. I know some of you have been working to a degree. Some of you did. I haven't heard from you. I hope you're washing your hands and keeping fine and working. So what I would like to do today is go through the Travelling Salesman Problem. Again, because I don't think we did a very good job first time round, and since we've got time, I thought we'll revise this. Use this video as a companion to the presentation that I'm also going to make available in Classroom, so you can sort of go along and see how you get on. All right? Okay, so here we go. I'm just going to let that animation play because why not? All right? Okay, so we're going to be looking at how to apply those three things to solving the travelling salesman problem. So remember that what the travelling salesman problem is about is someone that starts at a node of a network and has to return to the same node having visited every single node. And you've got two cases of the travelling salesman problem. You have to distinguish between the classical problem and the practical problem, okay? And the distinction between the two is there, and it should be pretty obvious what the difference is, okay? There. Now, you need to be aware of these key definitions, very clear in your mind what the differences are. Okay, again, they're just there, you can read them, there's no need for me to talk more than I have to remember. There is no algorithm to find an optimal solution to the travelling salesman problem, so what's going to happen is that you're going to find an upper bound for the total weight, distance or time of the problem. You're going to find a lower bound, and what you're going to try to do is to then narrow the gap between the upper bound and the lower bound until you get to a gap that you deem acceptable. That's like, okay, I can live with that difference between my minimum bound and my upper bound, okay? If you happen by design, chance or through work to find an upper bound that is equal to the lower bound, then you're sorted, then you have found the optimal solution. But more often than not, that is not going to be the case. Okay, before we do that, here you've got a simple network, and I would like you to find the table of least distances. Okay, you had a question like that in the last mock. Some of you got it very wrong, so pause the video, try to figure out what the table of least distances may look like, and then I will reveal the answer. I mean, you've got it on the slides, but please don't look at it. Pause the video now. Okay, hopefully you had a go and you would have found that that is your table of least distances. And big point, remember that there. Awesome. Moving on. Okay, now we are going to get into the meaty bit of it. For the travelling salesman problem, let's start with finding an upper bound. One way we can find an upper bound is by using the minimum spanning tree. So you're going to find the minimum spanning tree of your network either using prims or kruskals. Excuse me. Then you find the weight of that minimum spanning tree, you double it, because the idea being that you travel along the minimum spanning tree and then you come back, because you have to come back to the starting point. That's why we double it. And then we're going to look at trying to find shortcuts, okay? So Here is a network. Find the minimum spanning tree using Kruskal's, and then double the weight to find your upper bound estimate. Okay, so pause the video now and try to find the minimum spanning tree. I'm just going to go over there now. Okay, so I've got here the network that we had before. I am going to find the minimum spanning tree using Kruskal's. Remember, Kruskal's looks at edges, and we start with the shortest edge. Now the shortest edge is AD. So A to D for a weight of 3. I need to find the next least arc of least weight that connects two nodes in my network that I haven't got. The next one is CE. So C to E for a weight of 4. Then I need to pick one of the 5s, because that's the next least weight, and I could pick any of these 3 works because they are connecting nodes. I'm just going to go with BF. For a weight of 5, and then I'm going to choose. I've done this wrong. I have done this wrong. Okay. Prior to that, I forgot. We've got AD. Prior to the 4, I should have chosen AC, then CE, then BF. My apologies. This is tricky. There you go. Then either I can choose ED or no, actually, because I cannot have any cycles on my. So I cannot choose ED. I cannot choose CD because I will have cycles in the minimum spanning tree. So I cannot choose any of the 5s. So next, it's going to be DF for 7, and then it's only point G left to connect to my minimum spanning tree, and the shortest way to do that is from F to G for a weight of 8. That's my minimum spanning tree, no cycles. Remember that in the exam, you need to indicate which arcs you are not choosing when you go through Kruskal's, okay? Good. So my apologies for that, but hopefully that's clear. Then the weight of the minimum spanning tree, so the MST weight, is going to be 4 plus 3 is 7, 10, 17, 17 and 5 is 22, and 8 is 30. Remember, we double that to find the upper bound, so I get an upper bound of 60. That's my upper bound. I could have stopped there. Now, however, we could try to improve on that by using the shortcuts, right? So, if you think about this traveling salesman traveling through the network, let's say we started at A and we wanted to finish at A. I could travel doing A to C to E, so that would be 4 plus 3. Now, instead of going back, which is what we're doing when we double the minimum spanning tree, I could go straight from E to D, because that would be a shortcut, isn't it? If I did that, and I wanted to go I can just go across. So I would add the 5, and then I would do 7 plus 8 plus 8 again to go back, plus 5, and then to go back to 8, instead of going like that, I could just take the 9. Sorry, I'm going up. There you go. So if I add that, 4 plus 3 is 7, and 5 is 12, 19, 27, 35, 40, 49. I've actually improved on my upper bound by using shortcuts to 49. Okay? So there you go. That's one way to go about it. Let's go back to the presentation now. Okay. Sorry, moving around. So there we are. Another way that you could use to find an upper bound, instead of using double the minimum spanning tree plus shortcuts, you could apply the nearest neighbor algorithm. Okay? And you would do that multiple times. If you've forgotten how to do nearest neighbor algorithm, time to revise. You need to do it from the table of least distances, which is why we did it earlier. And in the exam, they're not going to ask you to do this for every vertex and compare and then choose the longest distance. It will take forever. But they may ask you to do it from one vertex only. Okay? But upper bound, nearest neighbor algorithm shouldn't be difficult now. Okay? So to recap, 2 ways to find an upper bound: using minimum spanning tree, double it, find shortcuts to improve, or nearest neighbor algorithm. Okay? Okay. Then, to find a lower bound using the minimum spanning tree, all you're going to do is, again, in the exam you're not going to do this for every vertex, but they may ask you to take your minimum spanning tree, take the full network, remove one vertex and all the arcs that link to it, okay? You find the minimum spanning tree of the bit that you got left of the network, and then you're going to add the vertex back and the 2 shortest arcs that connect it back to the network, okay? And if you do that for every single vertex, you will pick the highest possible value, because remember, you're trying to make the upper bound as low as possible, so your lower bound, you want it to be as big as possible to narrow the gap between the 2. So, if we go back to the board, let's explain how this might work. This is the network that we had before. So, we could take the network, say remove vertex B, and we will find if I remove B and find the minimum spanning tree for the remainder, I would have A to D for 3. I'm using prims now in my head, it's easier than cruscals. I would have AC for 3. I would have 4, I will have B now, so and then I will have D to F for 7, and then again F to G for 8. That would be my residual minimum spanning tree. I've removed B, so I'm going to add B back on to my residual minimum spanning tree and link it with the shortest 2 edges. So it would be that one there and the 8. It would be the 8. And the weight of this network would be my lower bound estimate for the Travelling Salesman Problem. So we'll have my lower bound, the upper bound that we found earlier, and we've narrowed the gap. Hopefully this makes a bit more sense. Go back through the chapter, try those questions, rewind the video, pause it, watch it again, watch it with the presentation. I know I've kind of run a little bit through it, but that's because I don't want to make the video too long, because I don't want it to take forever to load and you have it ready. Hopefully this made a bit more sense. Hopefully you got the slides, hopefully you got the video, hopefully you've got me walking through the example. I suggest you do it along with me as I go through it. Please message me if you've got any questions. I know you're going to be fine. You'll be fine. Please work, exercise at home. You need to keep mobile. You need to keep strong. Don't eat too much. Go up and down the stairs. Do some press-ups. Do some sit-ups. I don't know. I'll give you my training plan later. Have fun. Take care. Work hard. And I'll see you next week. Bye.